Electrostatics is made up of two words. Electro means electric field and static means still or that doesn't move. Electrostatics is branch of science which study of forces, fields and potentials arising from the static charges. In this chapter, we will learn about the properties of electric charges and fields. After completing this module, the students will be able to understand electric charge and its basic properties, explain the Coulomb's law, understand the electric field, calculate the electric field, understand electric field lines, define the electric flux, define electric dipole, explain Gauss theorem and its applications. Frictional electricity. What happened when amber rubbed with wool or silk cloth? In 600 BC, the Greek philosopher Thales observed that when amber rubbed with wool, it acquires the property of attracting objects such as small bits of paper, dry leaves, dust particles, etc. This type of electricity developed on the objects when they are rubbed with suitable materials is called frictional electricity. Attraction and repulsion. A famous American scientist, Benjamin Franklin, introduced the concept of positive and negative charges. He observed that when two glass rods rubbed with wool or silk cloth are brought close to each other, they repel each other. When two plastic rods rubbed with silk or cat fur are brought close to each other, they repelled each other. When glass rod is rubbed with silk and plastic rod are brought close to each other, plastic rod attracts the glass rod. From these activities, we can conclude that the like charges repel each other, whereas unlike charges attract each other. Electric charge. Electric charge is the additional property of protons and electrons which gives rise to electric force between them. Electric charge is a scalar quantity. A proton possesses positive charge while an electron possesses an equal negative charge, where E is equal to 1.6 into 10 raised to power minus 19 Coulomb. Detecting charge on a body. A simple apparatus used to detect charge on a body is the gold leaf electroscope. This apparatus constitutes following: wooden base, glass jar, gold leaves, brass rod, ebonite rod, metal disc, tin foil as cover, tin foils. Let's check whether the given glass rod is charged or uncharged with the help of a gold leaf electroscope. As the rod comes near to the ebonite rod, the charges from the metal disc pass on to gold leaves and the leaves move apart from each other. This shows that the given rod is charged. Conductors. The substances which allow electricity to pass through them easily are called conductors. For example, all metals like copper, silver, aluminium, and human, animal's body, etc. are good conductors of electricity. Properties of conductors. Conductors have electrons that can move freely inside the material. When some charge is transferred to a conductor, it readily gets distributed over the entire surface of the conductor. When a charged body is brought in contact with the earth, all the excess charge on the body pass to the ground. This process is known as earthing. Insulators. The substances which do not allow electricity to pass through them easily are called insulators. Properties of insulators. Most of the non-metals such as porcelain, wood, nylon, etc. are examples of insulators. If some charge is put on an insulator, then it stays at the same place and will not spread. A conductor may be charged permanently by induction process in the following steps. Take a conducting sphere, AB, with an insulating stand and bring a positively charged glass rod close to it. The end A of the conductor becomes negatively charged as the positively charged rod attracts electrons from the sphere, while the far end B becomes positively charged as positive charge repels positive. This process of inducing charge in a conductor without actual touching of charged and uncharged body is called induction of charge. Now, connect the conductor to the earth. The positive charge induced will disappear. The negative induced at end A of the conductor remains bound to it due to the attractive forces exerted by the positive glass rod. Disconnect the conductor from the earth, keeping the glass rod still in its position. The end A of the conductor continues to hold the negative induced charge. Remove the glass rod. The negative induced charge on the near end of sphere spreads uniformly over the whole conductor. In this experiment, the metal sphere gets charged by the process of induction and the rod does not lose any of its charge. We have discussed two types of charges, positive and negative. Point charges. If the charged body's size is very small in comparison to the distance between them, then we treat them as point charges. Some of the properties of electric charge are as follows. Additive nature of charges. The total electric charge on an object is given by the algebraic sum of all the electric charges distributed on the different parts of that object. Consider a system has n number of charges, Q1, Q2, Q3, so on up to Qn, then total charge of the system is Q equal to Q1 plus Q2 plus Q3 plus so on up to plus Qn. Charge is conserved. For an isolated system of many charged bodies interacting with each other, due to their interaction, the charges of the bodies may get redistributed, but it is found that the total charge of the system remains conserved or constant. For example, consider an isolated system of charges 2 coulomb, 5 coulomb, 8 coulomb, and 1 coulomb. Total charge of the system is 2 plus 5 plus 8 plus 1 is equal to 16. Due to the interactions amongst themselves, redistribution of charges takes place and charges become 4 coulomb, 4 coulomb, 2 coulomb, 6 coulomb. Now, the total charge of the system is equal to 4 plus 4 plus 2 plus 6, which is equal to 16. Hence, the total charge of a system remains conserved. Quantization of charge. All the observable charges are some integral multiples of elementary charge, E equal to plus minus 1.6 into 10 raised to power minus 19 coulomb. This is known as quantization of charge. The charges exist as the integral multiple of E. Look at the table to understand it clearly. Coulomb's law is the law of forces between electric charges. statement. This law states that any two stationary point charges Q1 and Q2 placed certain distance apart will repel or attract each other with a force F which is directly proportional to the product of charges and inversely proportional to the square of the distance between them. Mathematical expression. Consider 2-point charges Q1 and Q2 separated by a distance r in vacuum. The magnitude of the force F is acting between them. According to the Coulomb's law, force F is directly proportional to the product of the magnitudes of the charges Q1 into Q2 and inversely proportional to the square of the distance between them, that is, 1 by r square. Now this implies F is equal to K Q1 Q2 by r square. Let it be equation 1, where K is equal to 1 upon 4 pi epsilon node, when the two charges are located in vacuum. Epsilon node is the absolute permittivity of free space, which is equal to 8.85 into 10 raised to the power minus 12 Coulomb square per Newton per meter square. We know that 1 upon 4 pi epsilon node, after substituting the epsilon node value, will give 9 into 10 raised to power 9 Newton meter square per Coulomb square. Also, we can write equation 1 as F in vacuum is equal to 9 into 10 raised to power 9 times Q1 into Q2 by r square. Forces between multiple charges or vector form of Coulomb's law. Consider 2-point charges Q1 and Q2 at points with position vector r1 and r2 with respect to the origin. The magnitude of unit vectors r12 and r21 are as follows. Coulomb's law can then be expressed as F21 is equal to force on Q2 due to Q1. F12 is equal to force on Q1 due to Q2. We can see that both these forces are equal in magnitude but opposite in direction. Electric field. It is defined as the space around a charge in which any other charge experiences an electrostatic force. Electric field intensity. The electric field intensity at a point due to a source charge is defined as the force experienced per unit positive test charge placed at that point without disturbing the source charge. The mathematical expression is given as E vector is equal to F vector by Q node, where E is electric field intensity, F is force experienced by the test charge Q node. Its SI unit is Newton per Coulomb. Electric field due to a point charge. We have to find the electric field at point P due to a point charge plus Q placed at the origin such that its position vector OP vector is equal to R vector. To find the same, place a very small positive test charge Q node at point P. According to Coulomb's law, force on the test charge Q node due to charge Q is F is equal to 1 by 4 pi epsilon node times Q into Q node R cap by R square. If E is the electric field at point P, then E is equal to limit Q node tends to 0 F by Q node. And substituting the expression for F, we get E is equal to 1 by 4 pi epsilon node QR cap by R square, or E is equal to 1 by 4 pi epsilon node QR vector by r cube. Let it be equation 1. So, the magnitude of the electric field at point P is given by E is equal to 1 by 4 pi epsilon node Q by r square. Electric field due to a system of charges. Consider that n point charges Q1, Q2, Q3, so on up to Qn exert forces F1, F2, F3, so on up to Fn respectively on the test charge placed at origin O. Let Fi be the force due to ith charge Qi on Q node. Then Fi is equal to 1 by 4 pi epsilon node Qi Q node Ri cap by Ri square, where Ri is the distance of the test charge Q node from Qi. The electric field at the observation point P is given by following. If E is the electric field at point P due to the system of charges, then by principle of superposition of electric fields states that the total electric field will be the sum total of all fields. That is, using equation 1, we get the expression for electric field intensity for a system of charges. Electric field lines. An electric line of force is defined as a path along which a unit positive charge would move if it is allowed. Properties of electric lines of force. These lines start from the positive charge and end at the negative charge. They can never intersect each other because intersection implies that at a particular point, electric field has two directions, which is not possible. They do not pass through a conductor. They contract longitudinally. They exert a lateral pressure on each other. Electric flux. It is defined as the rate of flow of electric field through a given area. It is denoted by phi. Mathematically, electric flux of the electric field through a chosen surface is given as delta phi is equal to E dot delta S. This implies delta phi is equal to E delta S cos theta, where E is electric field, delta S is surface area, and theta is the angle between E and delta S. The direction of area vector is always perpendicular to the surface being chosen. Thus, electric flux is a measure of lines of forces passing through the surface held in the electric field. Total flux phi through a surface S is phi is equal to double integral over SE dot ds. Note, two integrals in this expression represents that the integral is taken over a certain area. An electric dipole is a system of two equal and opposite charges separated by a small distance. Electric dipole moment. It is defined as the estimate of the separation of positive and negative charges. It is a vector quantity. It is denoted by small p. The mathematical expression is given as P vector is equal to Q times 2A. Electric field on the axial line of an electric dipole. Consider a point P on the axial line of an electric dipole which is at a distance r from the center of the dipole. Then, electric field at P due to plus Q at Y is given by EY is equal to 1 by 4 pi epsilon node Q by YP square, and its direction is along YP. We can see YP is R minus A. Electric field at P due to minus Q at X is given by Ex is equal to 1 by 4 pi epsilon node q by xp square, and its direction is along px. We can see xp is r plus a. Net electric field is EP is equal to Ey minus Ex is shown as. Simplifying this expression further, we get EP is equal to 2 kpr by r square minus a square whole square, and its direction is along yp. This is the final expression for electric field. Electric field for points on the equatorial plane. Consider an electric dipole and a point P on its equatorial axis. The magnitudes of the electric field due to the charges plus q and minus q are given as. Therefore, E due to plus q is equal to E at minus q. The directions of these electric fields are shown. The components normal to the dipole axis cancel each other. The components along the dipole axis adds up. Therefore, the total electric field is given as E is equal to minus E due to plus q plus E due to minus q cos theta. Here, negative sign shows that field is opposite to P cap. So, E is equal to minus 2 qa by 4 pi epsilon node r square plus a square whole cube root P cap. This is the final expression for the electric field. Dipole in a uniform external field. Consider an electric dipole consisting of charges minus q and plus q and of length 2a placed in a uniform electric field E, making an angle theta with electric field. Force on charge minus q at x is minus qe. Direction is opposite to that of E. Force on charge plus q at y is qe. Direction is opposite to that of E. Electric dipole is under the action of two equal and unlike parallel forces which give rise to a torque on the dipole. We know that tau is equal to force cross perpendicular distance between the two forces. This implies tau equal to QE 2a sin theta, which on further simplification gives PE sin theta. Therefore, tau vector is equal to P vector cross product E vector. This is the final expression for the torque produced in an electric dipole placed in a uniform electric field. It represents the cross product of dipole moment P and electric field E. Linear charge density. When charge is distributed along a line, the charge distribution is known as linear charge distribution. It is denoted by lambda. The mathematical expression is given as lambda is equal to Q by L, where lambda is linear charge density, Q charge distributed along a length, and L is the length of the rod. Surface charge density. When charge is distributed along a surface, the charge distribution is known as surface charge distribution. It is denoted by sigma. The mathematical expression is given as sigma is equal to Q by A, where sigma is surface charge density, Q charge distributed on area A. Volume charge density. When charge is distributed over a volume, the charge distribution is known as volume charge distribution. It is denoted by delta. The mathematical expression is given as delta is equal to Q by V, where delta is volume charge density, V is volume of the conductor, and Q is charge on the lead. Gauss law. According to this law, the total electric flux through a closed surface enclosing a charge is equal to 1 by epsilon node times the magnitude of the charge enclosed. The mathematical expression is given by phi is equal to Q by epsilon node, where Q is charge Epsilon node is absolute permittivity. Proof of Gauss' law. Consider that a point charge Q is situated at the center of a sphere of radius a. According to Coulomb's law, E is equal to 1 by 4 pi epsilon node Q by a square a cap, where a cap is unit vector along the line OP. The electric flux through area element ds is given by d phi is equal to E dot ds, which finally gives d phi equal to 1 by 4 pi epsilon node Q by a square ds. Therefore, electric flux through the closed surface of the sphere phi is integration over d phi, which finally gives Q by epsilon node. It proves the Gauss theorem in electrostatics. Applications of Gauss' law. First, electric field due to a line charge. Consider a thin, infinitely long straight line charge of linear charge density lambda. Let P be the point at a distance a from the line. To find the electric field at point P, draw a cylindrical surface of radius a and length L. If E is the magnitude of electric field at point P, then electric flux through the Gaussian surface phi is equal to E into area of the curved surface of a cylinder of radius r and length L. As electric lines of force are parallel to end faces, circular caps of the cylinder, there is no component of the field along the normal to the end faces. This implies phi is equal to E into 2 pi AL. Let it be equation 1. According to Gauss' theorem, phi is equal to Q by epsilon node, since Q is lambda L. Therefore, phi is equal to lambda L by epsilon node. Let it be equation 2. From equations 1 and 2, we get the final result. E is equal to 1 by 2 pi epsilon node lambda by A. This is the final expression for the electric field. Second, electric field due to an infinite plane sheet of charge. Consider an infinite thin plane sheet of positive charge with a uniform surface charge density sigma on both the sides of the sheet. Let P be the point at a distance a from the sheet at which the electric field is required. First of all, draw a Gaussian cylinder of area of cross-section area A through point P. The electric flux crossing through the Gaussian surface phi is equal to E into area of the circular portions of the cylinder. Since electric lines of force are parallel to the curved surface of the cylinder, the flux due to the electric field of the plane sheet of charge passes only through the two circular portions of the cylinder. This implies phi is equal to E into 2A. Let it be equation 1. According to Gauss' theorem, phi is equal to Q by epsilon node. Here, the charge enclosed by the Gaussian surface Q is equal to sigma A. So phi is equal to sigma A by epsilon node. Let it be equation 2. From equations 1 and 2, we get E into 2A is equal to sigma A by epsilon node, which gives E equal to sigma by 2 epsilon node. This is the final expression for the electric field. Third, electric field due to a uniformly charged thin spherical shell. Case 1. When point P lies outside the spherical shell, suppose we have to calculate the electric field at the point P at a distance r when r is greater than r from its center. First of all, draw a Gaussian surface through point P to enclose the charged spherical shell. The Gaussian surface is a spherical shell of radius r and center O. Let E be the electric field at point P. Then, the electric flux through area element ds d phi is equal to E dot ds. Since ds is along the normal to the surface, so d phi is EDS. Therefore, total electric flux through the Gaussian surface phi is integral EDS, which is equal to E integral ds. Now, integral ds is equal to 4 pi r square. So, phi is equal to E into 4 pi r square. Let it be equation 1. Since the charge enclosed by the Gaussian surface is q, according to Gauss theorem, phi is q by epsilon node. Let it be equation 2. From equations 1 and 2, we get E into 4 pi r square is equal to q by epsilon node. This gives E equal to 1 by 4 pi epsilon node q by r square for r greater than r. This is the final expression for electric field. Case 2. When point P lies inside the spherical shell. In this case, the Gaussian surface encloses no charge. According to Gauss' law, E into 4 pi r square equal to 0. This implies E equal to 0 for r less than r. This is the value of electric field for this case. Let us summarize whatever we have learnt in this chapter. Electrostatics is branch of science with study of forces, fields and potentials arising from the static charges. Electric charge is a scalar quantity. A simple apparatus used to detect charge on a body is the gold leaf electroscope. The substances which allow electricity to pass through them easily are called conductors. The substances which do not allow electricity to pass through them easily are called insulators. Coulomb's law is the law of forces between electric charges. Electric field is defined as the space around a charge in which any other charge experiences an electrostatic force. Electric flux is defined as the rate of flow of electric field through a given area. An electric dipole is a system of two equal and opposite charges separated by a small distance